Hi everyone, I'm Joe. I'm a PhD student at University of California, Los Angeles. Today I will present our work on scaling up hybrid probabilistic inference with logical and arithmetic constraints via message passing. This is about probabilistic inference on hybrid domains, which basically means that we have both continuous and discrete variables. We also have complex constraints, which are both logical and arithmetic constraints. To perform probabilistic inference in these scenarios and to scale to large problems, we propose a message passing algorithm. To start with, let me convince you that it is important to model both continuous and discrete variables and constraints. Consider a skill matching system for online games. You have to model several players. For each player, he or she has a certain skill, which is a continuous variable, and these players form teams. So there are intricate dependencies between these variables. Moreover, to model the team performance, we need to introduce some constraints, saying that the team performance is a result of aggregating the skills of players in the team. And finally, to better describe the team performance, we also need to introduce discrete variables to indicate whether the players in the same team are friends or not, which we call the squad, because usually the team would have good performance if players know each other. Given such a scenario, you may want your system to answer such a question. What is the probability of Team 1 to outperform Team 2 if Team 1 is a squad while Team 2 is not? So, in the scenario we just described, we need to model both continuous and discrete variables and constraints over them. Then which probabilistic model can we use? Can we use the popular generative adversarial networks or variational autoencoders? Nope, because they have limited inference capabilities and they're not able to deal with constraints. Then what about classical probabilistic graphical models like the hybrid Bayesian network or mixed PGMs? Nope, because they're limited in representation power. They have strong distributional assumptions and cannot deal with constraints. There are more recent tractable probabilistic models, but still no, because they cannot deal with complex hybrid constraints. And instead, we use satisfiability modular theories, or simply SMT, which is a representation language over the linear real arithmetic that allow us to have constraints over continuous and discrete domains. It delivers all the ingredients we need by design, and it is also widely used in robotics, verification, and planning problems. Now let's go back to the previous scenario to see how to model the skill matching system with SMT. For the skill of each player, we introduce constraints. And this constraint says that the skill is a continuous variable bounded between 0 and 10. Then for the team performance bounded by the player skills, we also introduce the constraints. And this constraint says that the team performance xt is a continuous variable bounded by all the players in the team. And next, for the squad to indicate whether it is a good team or not, we can introduce a Boolean variable bs. And this constraint says that if the team is a squad, then the team performance xt is boosted. When we bring all these constraints together, what we obtain here is a single SMT formula in conjunctive normal form, describing the skill matching system. To further abstract the variable dependencies in the SMT formula, we could derive a primal graph for the formula. The primal graph denotes a variable in the SMT formula, and there is an edge connecting two nodes if the two variables are in the same clause in the SMT formula. An SMT formula, however, does not model uncertainty. We can make it probabilistic by defining the certain positive functions, called weights, associated to the models of a formula delta. An SMT formula together with these weight functions forms the weighted model integration model. We can think of this model as a distribution whose support is defined by the SMT formula and density defined by the weight functions. Then the task of weighted model integration is to compute the partition function of the unnormalized distribution. Here is the formal definition of weighted model integration, which we call WMI. Given an SMT formula and the associated weight functions, the task of weighted model integration is to compute the big integral shown here. Intuitively, what it does is to integrate over the weighted volumes of the visible regions defined by the formula. Let's go back to the aforementioned question that cannot be answered by the other models. What is the probability of Team 1 to outperform Team 2 if Team 1 is a squad but Team 2 is not? It's easy to answer it within the WMI framework. We first introduce two constraints here. The first one describes the condition Team 1 is a squad and Team 2 is not. The second one describes the query. That is, the performance of Team 1 is better than Team 2. Then the conditional probability will be the ratios of two weighted model integration. It tells us that in this case, Team 1 that forms a squad wins with probability around 58%. Now the question is how hard it is to compute the integral in the WMI task. Next, we will show some theoretical results about this. First, computing the WMI in general is sharply hard, since it involves solving an arbitrarily complex integration problem in high dimensions. A previous work showed that for WMI problems with tree-shaped parameter graph and for weight functions that are constrained monomials, there exists an algorithm that can reduce the problems to the unweighted ones and then do inference in polytime. We call the tractable WMI class in the previous work as tree-MI, and we put these problems in the graph here. This is the largest tractable class known so far. In our paper, we prove that even a slight expansion to the tree-MI could result in a sharply hard problem class, which we call 2MI here. There is the class of model integration problem with at most two variables in the class in the SMT formula. Now the question is, can we do better? Can we expand the tractable class from other dimensions? The answer is yes. We propose a WMI solver called Mpwmi, and it succeeds in expanding the tractable class. Now we show how our proposed solver works. Recall that for each SMT formula, we could define a parameter graph to describe the variable dependencies. And we frame tractable WMI inference at scale as a message passing scheme on parameter graphs turned into vector graphs. The vector graph formulation suggests that we could perform efficient inference in the classic message passing framework. It can process an upward and a downward pass. And during the pass, messages are sent from nodes to vectors and also from vectors to nodes. When this is done, we obtain the exact marginals for each variables. Given the explicit formulation of messages, this question naturally arises. Which parametric family should we choose for the weight family to guarantee tractable WMI inference? This question is important because weight family decides whether we could compute these messages both exactly and efficiently. We showed that to guarantee the tractability of WMI problems, the weight function family needs to satisfy some conditions, which we call the tractable weight conditions. The tractable weight conditions include that the weights should be closed under product, should be also closed under definite integration, and tractable for symbolic integration. Some example function families that satisfy tractable weight conditions include the general polynomial family, exponentiated linear function family, and the function family resulting from their product. By doing so, we are greatly expanding the class of weight functions you can use for tractable WMI inference. Another thing we can tell from the formulation of the messages is that the SMD formula induces a piecewise weight representation in the message. Here, there are three example messages generated when running the Mpwmi. This is strikingly different from the message passing for the classical PGMs. In classical PGMs, the bounded tree width is enough to guarantee tractability, while here, our complexity analysis shows that the number of pieces in the message could potentially exponentially grow along the diameter, even for a tree graph problem. And therefore, to guarantee tractability, we need to not only bound the tree width, but also bound the diameter of the graph. To summarize, our proposed solver Mpwmi is able to deliver efficient inference for the class of WMI problems whose graph has tree structure and whose weights satisfy the tractable weight conditions. We call this class as tree WMI. And it turns out that this class contains the largest tractable class known before and is the new largest class. In our paper, we compare Mpwmi with other existing solvers, a large set of synthetic benchmarks up to 100 variables, and different parameter graphs. For example, the WMI problems with star parameter graph with constant diameter, and snow parameter graph with diameter in log scale, and path parameter graph with diameter n. Over all these WMI problems, our proposed solvers shows a significant scale up over the other exact solvers like PA and FXSDD. Besides, our solver is the first WMI solver that is able to amortize over the query. A single message exchange allows to amortize both the univariate and bivariate queries. Not only Mpwmi can exactly compute in this way all the marginals, but also all moments for all the variables. From the curve, we can see that Mpwmi answers 100 WMI queries faster than the competitors solving 10. To conclude, real-world data is noisy, complex, and mixed continuous discrete. The WMI framework is very appealing for probabilistic inference in the real world. Our proposed solver Mpwmi is able to deliver fast inference and defines the largest class of tractable WMI models. However, Mpwmi requires the WMI problems to have tree-shaped and bounded diameter parameter graphs. And this is not true for all the real-world problems. And what's next is that we can build approximate inference schemes based on the Mpwmi solver. And if you're interested in the implementation, you can find our code here. And thanks for your time.